Now that you've had some experience playing with periodic functions and some horizontal scaling, we're ready to talk about sinusoidal functions. So first, we're going to look at some similarities between the graphs of the sine function and the cosine function. Then that's going to help us define sinusoidal functions. And then we're going to find the graph of a particular example of a sinusoidal function. So if we look at the graphs of y equals sine of x and y equals cosine of x, and here is y equals sine of x, and here is y equals cosine of x, it's easy for you, it's forgivable if you confuse the two because they look very similar, right? In fact, those graphs are identical if you ignore the x-coordinates. And in fact, if you look at the two graphs and don't ignore the x-coordinates, they look exactly the same, except they appear to be off by pi over 2 in the horizontal direction. And let's see, cosine is to the left of sine. So we get to cosine by doing a horizontal shift to the sine graph to the left by pi over 2, which means that cosine of x is equal to, well, let's see, if we're shifting to the left, that means we replace x with x plus pi over 2. So cosine of x is equal to sine of x plus pi over 2. So the sine graphs and the cosine graphs are exactly the same, just off by a horizontal shift. So the sine and cosine functions are examples of what we call sinusoidal functions. And so what is a sinusoidal function, the official definition? Well, the sinusoidal function is any function whose graph can be obtained by any combination of the following transformations on sine and cosine. So you can do a vertical reflection, you can do vertical scaling, that means stretching or compression. You can do horizontal scaling, which is horizontal stretching or horizontal compression. You can do a vertical translation, that is moving the graph up or down, or you can do a horizontal translation, which is moving to either side, either to the left or right. So you're doing these transformations on either the sine or cosine functions. So that means the formula for a sinusoidal function can be one of the following. Well, let's actually go through the process of doing those transformations. We're going to start with either sine x or cosine of x. We'll do sine of x, but if you do the exact same thing to cosine of x, that will also give you a sinusoidal function. So first I'm going to do a vertical scaling. That means I'm going to multiply my y-coordinate by a, so I get a times sine of x. I might do a horizontal scaling, right? So that means I'm going to replace my x with some constant times x. Then we're going to do a horizontal translation, which means I'm going to replace x with x plus a constant, a positive constant if I'm moving to the left, or a negative constant if I'm moving to the right. And then I might do a vertical translation as well. That means I'm going to move the graph up or down by adding a constant to the y-coordinate. So that is the general form of what a sinusoidal function can be. Of course, we can do the same thing to cosine, right? And we'll get the exact same type of formula. It'll just be cosine instead of sine. So that will also give us a sinusoidal function. And as you will see, I'm not going to demonstrate it in this video, but as we will see as we work through the examples in the activities, if we have a given sinusoidal function, that can be a sine or a cosine. That's mostly a matter of choice. Of course, we can do these transformations in a different order if we want. I'm going to go ahead and start with doing a vertical scaling as I did before, but instead of going right to a horizontal scaling, I'm instead going to do a horizontal translation. So I'm going to replace x with x plus c. Then I'm going to do a horizontal scaling, replacing x with b times x. Notice when I do it in that order, I don't have the parentheses around x plus c. And then I'm going to do a vertical translation. And of course, you can do the same with cosine. And I should say these give you the same types of graphs, because if you were to, in the first two graphs, take that b and distribute it through the x plus c, you'll get of the same form as h of x and k of x. But it is putting them in a slightly different form. So in general, our sinusoidal functions are going to be a times sine of b times the quantity x plus c, all of that plus d, or g of x with the exact same form except replacing sine with cosine. So I'm going to make some observations on what the different constants mean. What does a mean in terms of what it does to the graph? What does B mean? What does C? What does D mean in terms of the function? Well, again, A does a vertical scaling, either stretching or compression. So that tells us how vertically stretched out or compressed the graph is. And it also tells us how far above and below the vertical center of the graph goes. So in other words, the highest points get stretched out by a factor of A up. The lowest points get stretched out by a factor of A down. And so it tells us how much those get stretched out. And that is going to be what we're going to call the amplitude of the graph. So A is literally the amplitude of the graph. And we'll see how that actually factors into the actual graph of a sinusoidal function when we do our example. So what does B do? Well, B does the horizontal scaling, in other words, the horizontal stretching or compression. It tells us how horizontally stretched out or compressed the graph is, and that's going to affect how often the graph repeats itself. In other words, it's going to tell us what the period is. And if we remember how you figured out that formula from the in-class activities, that period is going to be 2 pi over b. So what does C tell us? Well, C just tells us the horizontal translation. How far to the left or right does the graph get moved? Again, a positive C means we move it to the left. Negative C means we move it to the right. And then D just tells us how far the graph gets moved up or down. That's our vertical translation. Now, when you're applying these to actual functions yourselves to try to graph a sinusoidal function, I got a little tip for you. It can be very difficult if you do the translations first. So in general, you want to do the stretching and compression, both the vertical stretching and compression and the horizontal stretching and compression before you do the translations. This will just keep your sanity. You can try doing it the other way to see how you run into trouble if you want. I actually mildly encourage you to do that, at least until you see where the insanity occurs, just so you can see why I'm giving you this advice. So let's go ahead and graph an example sinusoidal function. Let's look at 3 times sine of 2 times the quantity x minus 4, and all of that plus 1. We're going to do one transformation at a time. We're going to graph it, and that'll make it a little easier for us to handle those combinations. And I'm going to start with scaling, both types of scaling. I'm going to do the vertical, then the horizontal. Doesn't matter. You can do them in either order. So I'm going to start with y equals sine of x, and I'm going to do the vertical scaling first. First of all, I'm going to graph y equals sine of x. I start with that graph. And that's just we've graphed that before. We know exactly what that looks like. Now, if I put a 3 times sine of x, in other words, I do my vertical scaling, that means I'm going to stretch out the graph by a factor of 3. So that means all those highest points that go up to 1, those are going to be stretched out to positive 3. All those lowest points at negative 1, those are going to be stretched out to negative 3. Like this. Looks a little ugly, but we're doing the best we can. Next, we're going to do the horizontal scaling. So we're going to put in that 2. Now, replacing x with 2x is going to give us a horizontal compression by a factor of 2. That means everything is going to get skinnier by a factor of 2. So everything's going to be half as wide. So instead of, if you look at that 2 pi, that's going to come down to pi. If you look at that at negative 2 pi, that's going to come down to negative pi. The positive pi is going to come down to pi over 2. Then negative pi is going to come down to negative 2 pi over 2. And just in general, everything's going to be half as wide. Next thing I'm going to do is we can do the translations in either order. I'm a vertical guy myself. I like to do the vertical ones first. But if you like to do the horizontal ones first, they're no more difficult. It's just a matter of personal preference. So I'm going to do the vertical translation. That's moving it up by 1, so the y coordinates get bumped up. And then I'm going to do the horizontal translation. Since it's a negative 4, it's going to be moved 4 units to the right. Now you notice that the graph itself didn't move. What I did instead, this is a nice little trick that you can do as well, is all that is going to do is increase all the x coordinates by 4 if you're moving it to the right. So I added 4 to each of those points. So instead of pi over 2, you have 4 plus pi over 2. Instead of negative pi, you get 4 minus pi, or negative pi plus 4. And then there's our graph. So what I want you to also notice is that every sine graph and cosine graph has its center at the x-axis. Now I've moved things around. Now the new center, the vertical center, is right. See that red dashed horizontal line? That is now the center. In other words, it's halfway between the top of the graph and the bottom of the graph. And now that center, instead of being at the x-axis, is at y equals 1. That shouldn't be too surprising. We did a vertical translation of +1, so that's where that y equals 1 centering comes from. Just a good way to understand the position of our new sinusoidal function. So what that means is that the top and bottom of the graph are 3 units away from the center, and that is related to that 3 of our vertical stretching, or vertical scaling. And what that tells us is that the amplitude is 3. So remember I was telling you the A value always gives us the amplitude. Well, in this case our A is 3. That gives us an amplitude 3. That is, if you look at the center of the graph, it's 3 units up and 3 units down to the top and bottom of the graph. All right, so now I think that gives you enough background to start looking at some of your own sinusoidal functions. The activities that you want to look at are called graphing sinusoidal functions, and that's on the PDF file included with the video.